Hello, everyone. Thanks for joining. I'm Hao Lin from Greenplum7 China team. And today I will talk about Greenplum Fast Analyze. This is previously I just merged a feature. It's basically implemented for Append Optimized table and trying to speed up the analyze on AOCU tables. So. And this is the agenda. We will introduce some background information and also introduce some sampling method because this topic mainly focus on the sampling process. The sampling process is a sub-process of the analyze operation. So the fast comes from the sampling process. So this is the focus of this sub-process. And also we'll we'll introduce some high-level implementation and not too much detail. So, okay, next. So the background information. So as we know, analyze is an important operation, especially for optimizer, because it will collect some sample rows from the table and calculate the statistical information based on those sample rows, and then store them to some catalog. And the later queries will comes. The optimizer will based on those statistical information and build a proper plan to serve that query. Then the query may be performed efficiently. But if the statistical information isn't correct or isn't updated in time, the plan may be not efficiency. So this may impact the whole database performance. So this is the analyze purpose is important for the query performance. But previously, analyze on a large Append optimized table took a very long time because it behaves like a full table scan. If the table size is very large, the scan time gets longer. So it may crazy. It may be several minutes or more. That's not acceptable for customer. So this improving the speed of the analyze is highly desired requirement for the product. So this is the background. And okay. Firstly, I will introduce the sampling method for the upstream. Upstream using the sampling method for heap, for analyzing heap. The idea is for large tables, analyze takes random sample of the table contents rather than examining every row. This allows even very large tables to be analyzed in a small amount of time. The key point is even the table size is very large, but it will spend a short time to scan, to partial scan the table. So this could reduce the analyze time. Upstream using two-stage method. The two stages, first stage is select blocks. The second stage is select rows from previous selected blocks. So why upstream using the two-stage method? Why not? Because the analyze just select rows, why it still need to select blocks. So as my understanding is because for heap, we can know the total number of blocks, but we can't know the total number of rows. So maybe this is the factor that if we scan the row, if we scan the tables, if we don't know the total number of rows, we have to scan all the table. and that's low. That's very. This we could spend a very long time. So upstream using the two-stage. Firstly, it select the blocks from the whole table. It could it could use the micro relation get number of blocks. It could get the whole blocks number from the table. Also, the block size is determined. It is a fixed size block. Every block size is 32 kilowatts. So it could when it get a random block number, it could calculate the block offset in file to get to locate that block and then read the rows inside that block. So this is an idea from the upstream. When the first stage using Kuno's algorithm S to select blocks, this algorithm, the characteristic is it should know, it knows that the total number of space sampling, the sampling space. That means that the total number of the data site. So this is suitable for this fixed size block selection because we can get this total number. So so this is the first stage. And the second stage is using algorithm Z for selecting rows from the previous selected blocks. The total number of sampling space could be known or could be unknown. It just will, when the first stage, when selected one block, and the second stage will read all rows from this block, and to store temporarily to a reservoir like a pool to store these rows, and then continue select for further blocks and rows. And if the further rows is has better efficiency for better than the selected rows, it will replace the better one, and finally it will figure out the better selected rows. So this is a algorithm Z's workflow. So the problem of pre-existing method on Append Optimized table. So when we trying to use the two-stage sampling method for Append Optimized table, there is previously we didn't fully implemented that's a two-stage because there may be some complicated for at that time. So when doing row sampling, it's almost like a full table scan. For GP6, it was definitely performing a full table scan with algorithm Z. It will scan the whole table and using the sample rows number as the target size. So it will need to scan the full table and swipe the better rows for the based on the algorithm. And for all the main branch, that means without this patch, it looks like a two-stage, but it actually it doesn't. It's just select using the row, the target row number as the initial number of the block sample block number, and then select those based on those selected row number and try to scan the table. If the last sample row number fall around the end of the table, that's the mostly like this, and it will have to do the full table scan, most likely. So this is a problem, and for because the block-based sampler doesn't work well on this variable length block storage, because our append optimized table is a variable length block. So the first stage, when using variable size block, is unable to calculate the physical location of a sample row, of a sample block like heap, because we can't calculate the location based on a variable size block. Without that block location, we can't read the tuples inside the block. So this is a problem. And a proposal from community introduced a logical block concept. That means using the fixed number row as a fixed size block, like a fixed size block to fit the algorithm S. Firstly, the first stage is looks like when select number of blocks, it will select from these logical blocks. And since this logical block is a fixed size block, because they contain fixed number of rows. So, and then the second stage is just using the algorithm theme to select rows from these logical blocks. And another improvement is they are using a header-only scan for the var block, because var block consists of a header and content. When we read the header, it just do normal read, and if we need to read the contents, usually the content was compressed, so we have to decompress this, do a decompression, and then read the content. So the decompression may spend much time usually. But for this method, it's because between the first and the second sample blocks, the blocks between those two blocks, we can just read the header only. We can just read the header, but no need to read the content, because we actually know there's no sample rows between these blocks. So this is a idea to improve the speed. And but there's still a problem that if after we selected the first the blocks, we need to select rows from these blocks, but because we need after the final row set should be ordered by physical location. That means this is very important for later column correlation calculation. It depends on the tuple location. But if we are using the algorithm Z, it will replace the previous selected rows. So it will disrupt the physical order of the tuple. But unfortunately, Append Optimized table memory tuple doesn't store the tuple TID. This caused the resorting unavailable. We can't, because the tuple TID has the location information like block number and row offset, like heap. But for Append Optimized table, the memory tuple just stores the content, but no metadata. So this is a problem. This makes the algorithm Z unavailable for now. So next. So what's we are using for the analyze AOCO tables? We analysis about the Append Optimized table, the specific feature like total number of rows, we could be known easily by catalog lookup, like PG underscore AOSEG catalog. There's some tuple count stored in there, and we can we can just collect those tuple count for per segment, and then sum them together. Then we can get the total number of tuples of the table. And we also have tuple fetch facility that's supporting locating a variable block without decompress all the preceding data. That means like an index scan. When we firstly read the index, we get the tuple TID, and using the tuple TID, we jump to the location of the physical blocks and read the tuple. This is the feature of the Append Optimized table. And we also could leverage block directory, because the block directory stores some meta information of every var blocks, providing first row number to file offset mappings. This is a very important number. This is very important mapping because we scan the block directory and we got the block first row number, but how we still need to know the first block file offset corresponding to the first row number. Then we can jump to that blocks. Otherwise, we can't. So this is a very important information we can leverage. So the final solution is, seems all above features indicate operating a row is more easier than operating a block on Append Optimized table. Yeah, I think actually Append Optimized table is row more. The concept is more friendly to row, but not that friendly for blocks. So I think maybe it's not necessary to have a block level sampler. The advantage of having a block based sampler is we don't need to have to scan all the table. We just scan a part of the table. We can get the sampling space. So the sampling space is smaller than the total scan full table. So this is an advantage. But for now, I think because we don't store tuple TID in memory tuple, we don't have a way to sort based on that. So I think currently maybe not necessary for block level sampler. So the choice is no block-based sampler and just directly use the Greenplum7 implementation as a row-based sampler and no need resorting. So maybe someone has concern about Greenplum7. Yeah. The Greenplum7 maybe doesn't work well for the large data sets. Maybe it's not that fair enough as a sample for every sample rows. Also, there's maybe some performance problem if doing Greenplum7 in a large data set. But for upstream, the implementation of Greenplum7 is different from the original ones. It's doing some engineering improvement, like it skip blocks if the blocks wasn't sample block. So it's just doing the Greenplum7 on those sample blocks. This is an improvement of the performance. So we don't need to invoke the random value generator every time for every blocks. For every block, when invoke a random value generator, is for every block it's very low efficiency and may performance bad. But if we just select just invoking random value generator for those sample blocks, because the sample block is a fixed number, so we every time just the cost can be converted. So yeah, so this is the advantage for the upstreams implementation. So yeah. So finally, we choose the algorithm S and use it to row-based sampler. Okay, next. So the implementation, because there's a very different storage layout between heap and Append Optimized table, and also also some senior engineer like Hiki just recommended using table AIM to abstract this implementation based on different storage layout. So we just introduce a table AIM API for Append Optimized table for this sampling method. And also because we are using the algorithm S, the original algorithm S using integer 32-bit to store the block number, but currently the row number is exceeded this scope. So we are using 64-bit integer to store the number of rows. So just a copy of block sampler and change the type. So we have two cases. One is a var block based analyze, and another is block directory based analyze. Because block directory based analyze requires block directory existed. But if there is no block directory, means no index, we have to do a var block based analyze. So for var block based analyze, we just perform, we just scan the required sample blocks header and also decompress those sample blocks, those content and read the tuple, but we don't need to decompress a non-target block. So and for var block based analyze is the workflow is firstly locate the target segment file number. As we know, we can get the file number. We can, based on the input, the input of the method is it will input a target row. This target row number is a logical continuously row sequence starting from 0. Then like row 1, row 0, row 1, row 2, row 3, and row something. So we can, based on this info, to calculate, to locate the target segment file. That means which segment covers this target row. And next, we just do scan var block headers by trying to based on this information and also block first row number and the block row count to get the distance to the target row. Then we just from the var block header, we can get those information and we can get the result if the target row fall in this var block or not. And just skip those non-covered var blocks. And then when we locate the target var block, we just do the decompression for this var block and read the tuple. So this is the detailed calculation for this. We just introduce some control vars for tracking the currently what is the row number we are at, and then doing that, and then to compare with the target row to compute the distance. So after we got the target row number, that means that after these steps, we can get the mapping from the target row to the to convert this target row to a row number. when we get a row number, we can figure out the tuple TID. That means that because it consists of a segment number and a row number, so we can figure out this. And when we have a tuple TID, we can do many things like do visibility check and also fetch the target tuple based on this tuple TID. So this is a var block based implementation. The next, for the block directory based analyze, firstly, we have created the block directory, and also we firstly need to locate the targeted segment file number. And then we have because the block, when we need to scan the block directory, the key, we using index scan the block directory. The key consists of three attributes. One is the segment number, and second is the column group number. I mean the column number, and also the first row number. We don't know the first row number, but we know the previous two one. So previous two attributes. So when we get the segment number and we also know the current row column number. So we can do index scan based on this case and get the corresponding mini page. Because the block directory is stores entries in mini page. The record is based on mini page, and the mini page stores mini page entries. So when we get the mini page entries, like one entry, mostly like mapping to a one var block for simply understanding. Yeah. So when we get the corresponding mini page, when we can get the corresponding entry, and the entry stores some like block first row number and also file offset, and also the block count. So we can get the target block first row number, and we know the offset, the file offset. And based on the first row number, we can get the distance between the current target row to from this first row number. We can know if the target row is covered by this var block or not. So when we find the target block entry, then we will jump to the corresponding var block offset to read the physical var block and to decompress the content and fetch the tuple. We just form this tuple TID and pass it to the index fetch interface to get the target tuple. So this is a block directory based analysis. It's more performant than var block based analysis because it's no need to scan the sequencer scan all the block headers. It's just jump to the target block and read the tuple. So, okay. And some sample test. Previously, we have the almost 1 minute scan for this size table. After implementation, after patch this implementation, we spend just no more than 3 seconds. So it's much better. And with a block directory based and catch warm up, and we can get more short time for the analyze operation. It's mostly close or better comparing with heap. So this is we have done. And okay. So most of the information could be found in the PR. Well, we have some discussion around this algorithm, several discussion, and also many review comments and contacts for this implementation. Okay. Okay.